Mabel, what's up?
Hello, hello, how are you?
Fine, how are you?
I'm good, I'm great.
Good, good. You excited? You ready?
Yeah, I'm ready. Let's do it. Let's
Nice.
go.
You look nice. I like your background.
Thank you, thank you.
I always like when there's books in the background. I think even during interviews, I feel like some of the interviewers would always like comment on like the books in the background, those kind of things. Even if it was like some random, I had like some fantasy books, I think, in the back, like nothing medical. And they'd always be like, "Oh, that's nice. What kind of books do you read?" And it's always like a talking point. So I think it's always nice to have different things in the background. Just
I
kind of.
also have this thing that says pick me.
Yeah, yeah, yeah. Exactly. I like that. Yeah, yeah, yeah. I like that. That's awesome. That's funny. Cool. So yeah, we'll give it a few more minutes. And then probably right at six or a little bit after six, I'll introduce you. And then I'll let you take over from there. Like you said, I think you were saying 6:40 might be a good time to just give everyone like a 5 minute break. And then, then we can, if they have any questions or whatever, and then we can just end it with some quizzes, or I think you had some quizzes, I think is what I remember you said, right?
Yeah, I have some questions for
Okay,
you.
yeah, yeah. So just some questions. Like I said, I'll be on in the background, just kind of navigating any of the questions that people may have if they want to post in the chat. I know sometimes people are shy, so
Okay.
I'll be in the chat, and then I think this thing goes for hopefully over an hour because I have the pro account. But I've heard sometimes they cut short at like 40 minutes. If anything, I already have a backup link sent. Like I'll just forward it in the group so everyone can just link over at that. But and it'll be right at the 40 mark, which will be that 5 minute break anyway, so it works out. But
Okay. And then for sharing my screen, I think
yes.
you have to give me access to
Oh,
that.
good, good, good. See, that's why we get on early because let me see. Do I have multiple friends? Share some things? All right, cool. Yeah, I think you should have access now.
Okay, cool. Awesome.
Yeah, cool. Perfect.
So just wait around.
All right, now let me see who's in the chat. 'Cause I know I invited a whole bunch of people, so this is 7A. I like it. Okay. We got some people. Probably some stragglers.
Just let me know when.
Yeah. We'll give it a couple more minutes. Mhm.
Maybe I can put a little.
Sorry, say it again. You're a little muffled. What were you saying?
Yeah, maybe I can play a little music.
Oh yeah, if you want. What has to be webinar appropriate. I'm not sure. What kind of music do you listen to? Actually, I don't think I've ever asked that.
Play some classical music.
Okay. Fair, fair, fair.
Just while we wait.
Uh, dope. Okay. Dope. All right. Honestly, I think we should be good to go. No worries. Okay. Yes, yes. Consoles. Okay, cool. All right, you know what? Let's get this started. All right, cool. Thanks for joining everyone. As you're hopefully you're aware, I'm Dr. Simpson, CEO of Top MD LLC. I put this thing together because I think just along the way of just my many years of tutoring, I found that like a focal weak point for a lot of students, even myself when I was taking the boards, is really biostats and epidemiology. And those are really, easy points if you just put in a little bit of the work, but they go a long way. I found a lot of times that we've kind of had some of these sessions before with our students, and they've actually understood the concepts. Their scores have improved significantly for their boards, and this is across the boards. Whether you're taking step one, step two, or even step three, you're going to see biostats and epidemiology on all those boards. I just took my ABIM boards for internal medicine licensing, and I still had some biostats questions on there. So you never get rid of it, basically. So, I was kind of looking and trying to figure out, how we can do kind of a quick overview, especially as a lot of you are preparing for your upcoming respective exams. Then I met Dr. Kimble, and she's such a phenomenal person. I've had the pleasure of knowing her for maybe just a few weeks now, but we've grown very close, and she's smarter than I am. And so, just let me, I just want to introduce her. And then basically what's going to happen is after I introduce her, she's going to take over, and she's actually going to really just run you guys through a crash course of biostats and epidemiology. And like I said, feel free to take notes, write things down. I will be monitoring the chat. I'll have my video off, but I'll be monitoring the chat. So if you guys have any questions, feel free to just kind of text in there, or if you, really have an urgent question, ideally, if you can wait till the end, we'll have a session or have some time at the end where we can ask questions. Um, and so, or if you really just need it, just text in the chat, and then I'll see if I can answer it. There's going to be a bit of interaction as well. Dr. Kimball will have a few questions that she'll kind of just post in the group, and feel free to share. Like I said, this is a very relaxed environment. I'll try and come in and offer some tidbits. I'll try and answer some questions. I'm sure I'll get most of them wrong. So, don't feel like we're like testing you or anything like that. This is really just for your guys' benefit. So without further ado, let me introduce Dr. Kimball. So Dr. Kimball is a physician, educator, and researcher, and passionate mentor with a strong background in biostatistics and epidemiology and clinical research. She has trained at world-class institutions, including Cleveland Clinic, Jackson Memorial Hospital, Henry Ford Health, and Danbury Hospital. Beyond medicine, she has dedicated herself to education, teaching anatomy, forensic science, and coaching students through their board exams. So, like I said, I just want you guys to give a warm welcome to Dr. Kimball. Dr. Kimball, please feel to take over.
Good evening, everyone. And thank you, Dr. Simpsons. You truly appreciate the introduction. When I first uh, heard someone uh, say my intros, I couldn't believe it. But yeah, that is me. I'm really happy to see everyone here, and thank you for joining us. Again, my name is Dr. Kimball, and I'm truly thrilled to be here with top MD tutors for our comprehensive overview of biostatistics and epidemiology. We have an hour today, and I'm going to try to go over as much as possible. I'm sure we're not going to be able to go over everything, but we'll do as much as we can. Tonight, our approach will be intentionally stepwise. We'll begin with the most basic building blocks. Let's see, okay. Most basic building blocks, core concept, vocabulary, intuition, and then we'll steadily build toward the equation, decision rules, and testing strategies you are expected to know for the USMLE. What I've found, though, time and time again, is that when we understand the underlying purpose of these tools, the problems they were designed, the problems that they were designed to solve, and the assumptions they rely on, the formulas stop feeling mysterious and start reading like common sense. So by anchoring every calculation to a clear idea, those expressions that once looked intimidating become straightforward, okay, usable, and even intuitive. So with that in mind, we're going to jump in and start connecting principles to practice. Okay, so this is our roadmap. This is our part one. We're going to start talking about why statistics matters in medicine, why we even bother describing data, and what um, and why we even bother describing data, and what key distinctions exist within it. So understanding those distinctions is critical because they form the foundation of everything else. Second, we'll look at how those distinctions directly inform the type of tests we use and the way we design studies. After all, the goal isn't just to collect data, it's to collect the right data in a way that makes it suitable for proper analysis. And finally, in the third part, we'll bring it all together. We'll walk through how these concepts are tested on the USMLE, and even more importantly, how they show up in the real clinical practice, okay? Because at the end of the day, these aren't just exam tricks. These are tools you rely on as a physician to make evidence-based medicine decisions for your patients. First, let's think about the difference between accuracy and precision. On this slide, you see, let me see if I have access to annotate. Okay, on this slide, you see on this dartboard example, it's very, very classic. We've seen this in all of our USMLE exam books and throughout medical school. And it's a classic way to visualize this. Precision, sometimes I have a hard time saying this word, basically means hitting the same spot over and over again, regardless of whether it's the bullseye, okay? I like to think about this as a broken clock. A broken clock is highly precise. Every time you look at it, it gives you the exact same answer. There's no random error. It's perfectly consistent. It's right twice a day, right? So the problem with a broken clock is that it's only correct twice a day, and that makes it precise but not accurate. All right. And so now when we're talking about accuracy, accuracy, on the other hand, is about getting the answer that reflects the truth. So again, precision is something, as you know, hitting the same spot over and over again, and accuracy is getting the answer that reflects the truth. Okay, so hitting close to the bullseye. So you can be accurate without being very precise. For example, you can think about a friend who is very outspoken and tends to make bold statements. Okay, and sometimes they hit the truth right on, but other times they're a little off and create friction, right? So they might be accurate in spirit, but not always precise in delivery. Okay, so this is what it looks like to be precise, and this is what it looks like to be accurate, right on the bullseye, and then precise, you can outside of that. Now in medicine, especially when we're diagnosing patients, what we really want is both, right? Accuracy results, again, results that reflect the truth, and precise results that are consistent and reproducible. And that combination is what gives us confidence to rely on a test or measurement when we're making decisions for our patients. All right, guys. So now what happens if we realize that a test has a problem with accuracy or precision or both, right? So if a test has low accuracy, if a test has low accuracy and low precision, my approach will need to be completely different than if it only struggled with one, right? Some tests are highly accurate. They reflect the truth on average, but they may be a little less precise, meaning the results bounce around more from trial to trial. Okay, so these are the different instances where you can have accuracy that is low and precision that is low, and then also another case where you can have an accuracy that is high with low precision. So these are the cases that can be possible. Okay. And so on the flip side, some tests are very precise, just like this example here, in this example here, they give nearly identical results each time, but they may consistently miss the truth, making them less accurate. So sometimes in medicine and research, we have to recognize that there's trade-offs between these qualities, okay? That trade-off becomes especially important when choosing diagnostics tests or interpreting results. The key point right now is just to acknowledge that these limits exist, and later in the course, we will build on this idea and talk about how to deal with these trade-offs when you're selecting and interpreting tests, okay? And this is all going to make sense a little bit more as we go through, but I wanted to explain this slowly so that you guys can understand it and apply it to your questions, because that's what the USMLE expects of you. Let's go to the next section. Okay, so now in that spirit, let's step back and ask, why do we even use diagnostic tests, right? So the ultimate goal is simple, really is to figure out who actually has condition or disease, okay? So, but when we talk about disease in population, we need to use two key measures that you see in this slide. We're going to talk about prevalence and incidence. So prevalence here, prevalence is the total number of people who have the disease at a given time. Okay, these are people who are already sick, right? And then incidence is the number of new cases that occur within a defined period. So these are people that just got the disease, new cases, okay, over the people that are at risk for the disease, okay? The distinction is critical for doctors, right? Because this is something that we have to pay attention to. Let me give you an example. COVID in early pandemic, the true danger wasn't just prevalence, right? It wasn't that everyone had it yet. The problem was the incidence, right? The number of new cases exploding every day for COVID, or expanding every day for COVID, the surge in incidence is what forced shutdowns and led COVID to be classified as a pandemic, okay? Now, another example, Ebola, right? During outbreaks, incidence is extremely high. Cases rise rapidly, but prevalence remains low, right? Because unfortunately, most infected patients die within about 2 weeks. So you can see here the relationship between prevalence and incidence, right? So for Ebola, you're going to notice that, you know, some of these patients are going to die, right? And that's going to, they're going to have high incidence, but these prevalence are going to be low because they're basically dying off, right? And for COVID, what's happening is that people at the time were getting new cases of COVID. And now another example is chickenpox. On the other hand, right? Chickenpox is the opposite story. Anyone here above 40 probably remembers getting chickenpox as a child before the vaccine was available. Okay, so that makes chickenpox a disease with high prevalence, right? So someone 40 years old who got chickenpox when they were a child, right? And that makes chickenpox high prevalence, right? But today, thanks to vaccinations, right? Thanks to vaccinations, that the incidence is very low, right? Few new cases occur each year. So prevalence and incidence tells us very different things. One describes the overall burden of the disease, which is our prevalence, while the other describes how quickly it's spreading right now, right? So now let's pause here because I'd really like to interact with you guys. I don't just want to talk the whole time. You know, as a student, I wanted, you know, I would always feel like I was bored when I heard my professors talk all the time. And so I wanted to incorporate some answer question here. I want, this is a safe space for everyone. I'd like to just ask you a few questions about, think for a moment, how do changes in incidence or prevalence affect how we see disease in the population? So if anyone could, raise their hand or volunteer, I'd like to know if you know what happens to incidence or prevalence if you increase survival time.
Hi, I'm Yasmin. Um, so in regards to increase of survival time, the incidence I think would just stay the same, but prevalence would go up because there would be an increase in patients that still have the medical condition, still alive, still thriving. So it would seem that the number of existing cases
Mhm.
would increase, but the incidence would be like at a stable rate.
Exactly. That's exactly what it is. Thank you, Jasmine. I appreciate you, participating. Really appreciate it. Now, is anyone here would like to answer the second question, which is what happens to incidence and prevalence when you increase mortality?
Wouldn't the incidence still be the same, but would have a decrease in our prevalence?
Exactly. That would be an Ebola situation, right?
Mhm.
Um, what about uh fast recovery time?
I don't mind going again. I believe that in regards to incidence, I think it would still be the same, but prevalence would go down because the number of patients with the condition would decrease since they're recovering.
Yes, perfect. Thank you, yes. And then what about vaccination administration, extensive vaccine administration?
I'll go. Oh, excuse me, I'll go. I believe that vaccine administration would decrease the incidence
Mhm.
and it would also decrease prevalence, I want to say.
Exactly. Good job. Thank you. Say your name again for me.
Oh, my name is Fauna. Sorry.
Thank you for answering the question. And then our last question for today, not for today, just the last question on the slide. Decrease risk factors.
Hi, my name is Sukhwinder.
Hmm.
Um, I think the incident and prevalence will both decrease.
Yeah, awesome. Thank you so much. I do appreciate everyone participating. I know that it can be scary, but please, this is a safe space. We're all learning. I was in your position not that long ago. I really want this to be an interactive space for us because I want you guys to really learn this stuff because biostatistics, as you go, especially for the USMLE, step two, in addition to biostats in the social science portion is about 15%. And in step three, they, go up even more. So thank you for participating. I want you guys to really understand this, okay? And we're gonna break it down as much as we can. All right, so let's do a quick recap. So here's a summary of what we just covered, right? So prevalence is the total number of people who currently have the disease or condition. Think of it as the overall burden in the population. And then incidence is the new cases that occur in a given population during a specific time period. Think of it as a rate of spread. Okay, so if you're ever unsure, prevalence is who has it now. Okay, think about it in that way. And incidence is how many new cases are showing up over time. This is the foundation of everything else we'll be building towards in diagnostic testing and epidemiology. Okay, so let's go to the next slide. Hopefully this makes sense. So now that we've identified who has the disease and who doesn't, the next step is to think about how we can describe the overall group. Okay. In statistics, we have two very useful ways to summarize data. So we have first measures of the center or measures of central tendency. These tells us the typical or usual value in the group. In other words, what number best represents the middle of the data set, okay? Number two, measures of dispersion, okay? These tells us how spread out the data are. Do most people cluster tightly around that central value, or are the results more scattered? So when we're describing a group, we're really asking, what is the most representative value? And how consistent or variables are the rest of the values around it? Okay, and we're going to take a closer look at each of these details. And then I'll also talk about normal distribution as we go, and this will all make sense, I promise. Okay, so when we describe a data set, one of the first questions we ask is, what is the typical or central value, right? There are three main ways to measure this. We have our mean, median, and mode, okay? Our mean, the average, this is the one you probably learned first in school. You've heard of this a million times, right? You add up all the values and divide by the total number. Simple, but there is a catch. And that catch we need to understand. The mean is very sensitive to outliers, okay? Think about your grades, right? That you've gotten over your medical school journey, or even, back when you were in grade school. No matter how many good quiz scores you have, if you get 1-0, your average will drop dramatically. That single outlier can distort the picture, and means are very sensitive to that. And outliers, it's a very testable concept in the USMLE. We're going to see that in one of our practice questions later. So this is something you should be aware of, okay? And then median is less affected by outliers, okay? If you have 9 quiz scores, the 5th one in order is the median, right? So the 5th one will say 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So this 5th one is the median, and there's going to be 4 below and 4 above. So if you bombed your first quiz with a 0, the median still reflects your typical performance better than the mean. That's why the median is often preferred when in skewed data sets. Okay, and I'll show you some of the skewed data sets a little bit later. It's probably in the next slide or two. And so you can see what I mean by that. And then the mode. The mode is the most frequent value. So if you have like a set of data like this one I just showed you, you'll see 5, 5, 5 most often, and that is your mode. Okay, and this tells you what happens most often, right? So mode is particularly helpful when you have a categorical data or when you want to highlight the most common outcome. And the most testable concept here is that this is the least affected by outliers. So if you had to rank these, you would say mean is most affected, then median, and then so it'd be mean, median, and then mode. Okay, so that's how you would categorize that in terms of outliers. Okay, let's move on to the next slide. Okay, so before I move on to the next slide, I wanted to bring this point home for you a little bit. So here are a few nuances that I wanted to give. So sometimes we want outliers to matter. Like, for example, Maybe this will make a lot more sense. If the outlier in real life situation is death in a clinical trial, that's not just noise. That is highly relevant. So you don't want to ignore that outlier, right? In other times, the outlier isn't meaningful. Like that first week zero when you were still trying to figure out how to study. Okay, so the mean, median, and mode each have their place depending on what questions we're asking and how much influence we want outliers to have. Okay. Now that we talked about the center of the data, the next question is, how spread out are the values around the center? Okay, this is where measures of dispersions come in. The most common one you'll see, and the one that shows up constantly in studies and on exam, is standard deviation. Standard deviation tells us, on average, how far each data point is from the mean. In other words, are most values clustered tightly around the average, or are they widely scattered? Okay, so it's gonna make sense later too. So are they tightly around the average? This is the mean, tightly around the average, right? Or are they spread out? Okay. So a small standard deviation means that the data points are close together, right? So this data points are close together, right? And the mean is a good representative of the data set, right? Because they're very close, right? A large standard deviation means there's a lot of variability. That means alone, it doesn't tell the whole story. And you'll notice that in almost every published study, the mean is reported alongside the standard deviation, right? Mean, so they'll say mean plus or minus SD. Okay, that's how usually they would report it. That's because together they give you both the center and the spread of the data. And on the boards, being able to interpret the standard deviation is key because it ties directly into normal distributions, just like we're going to talk in the next slide, z-scores and confidence intervals, which we'll get into. Okay. So now, outside of medicine, we're going to talk about what they call the standard error. But I want to give you an example before I tie that into standard deviation and standard error. I want to give you an example of that that will help you understand it. Okay. Outside of medicine, think about visiting an ice cream shop, right? You can have a full scoop of every flavor. You don't have, you can't have a full scoop of every flavor, okay? You don't have the time, the money, or stomach space, but you can ask for a sample spoonful, okay? The key is that the taste of that sample reflects what you would get in a full scoop. Hopefully that makes sense. So if you have, this entire bucket of ice cream, and then you're at an ice cream shop and you get just a spoon of it. Sorry, I draw really bad. Okay, the key is that the taste of this sample reflects what you would get in a full scoop, okay? That's the role of statistics, right? To find a sample that represents the larger whole, right? The whole point is to get a sample to represent this entire thing. Ideally, when you're studying a disease, we'd want to know about every single case in existence, okay? That's the true population, right? So this is the true population, but that's impossible. It's too expensive, too time consuming, and limited by our ability to diagnose and process all the data. Instead, we take a smaller sample, this scoop, okay, under conditions that we hope are representative of the larger truth, right? We hope that it is representative of this big tub of ice cream, right? So when we talk about data, the real question becomes, how close is our sample? How close does this sample mean? Okay, let me relate that. Right? We're talking about the mean of this sample we took to the population mean, right? To this larger truth, right? This is our the full scoop, right? So we're just taking a sample of that, right? So again, the question becomes, how close is our sample mean to the population mean? Or in ice cream terms, that's the taste of one spoonful reflects the flavor of the whole tub. Okay, now let's build on that and move on to the next slide. Okay, so we're going to build on a standard deviation by talking about something closely related, which is the standard error. All right, so the standard error is essentially an estimate of how far the sample mean is likely to be from the true population mean. Okay, what we just talked about. So how far is the sample of that ice cream from the tub of the larger truth? Okay. So mathematically, this is the, so basically mathematically, this is the formula we want, right? Standard error equals standard deviation divided by the square root of the sample. Okay, that means that larger your sample size, right? So let me do this way. So you can, so it will make even more sense, right? So here's n, right? So this means that the larger your sample size, the smaller your standard error, right? So this is an inverse relationship. So if you increase the sample, you're going to decrease the standard error, okay? So basically, the more people you study, and they love to ask this, what's going to increase the power, blah, 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 blah. If you increase, the reason why is because you increase your sample, you increase the standard deviation, the standard error, which means the data are close together, okay? So the more people you study, the more confident you are that your sample mean reflects the truth, okay? Let me say that one more time. The more people you study, the more confident you are that this sample reflects the truth, reflects the population meaning, okay? So this is why large clinical trials gives us much more reliable estimates than small pilot studies, okay? Usually when we describe a data set, we pair them with mean, with either the standard deviation, or in some cases, the standard error. Together, these tells us both the center of the data and how tightly or loosely the data are spread. Okay? Now we're going to apply that to different distributions. So this makes sense. All right. So now, let's apply this to the most important shapes in statistics, the normal distribution, also called the bell curve. Many biologic measures like blood pressure, height, cholesterol, tend to follow this curve in general population, okay? The beauty of normal curve is that it's symmetrical, okay? Data are equally spread to the left and right of the mean, right? So this is our mean. So it's going to be spread left and right, left and right of the mean. So this allows us to make precise probability statements about where most values fall. Like, here's the classic rule you need to know. They like to test this on the USMLE, okay? Here's the classic rule you need to know. 68% of the value, 68% of the value will fall within 1 standard deviation. 95% of the value, right, fall within 2 standard deviations. 99.7% of the value will fall within 3 standard deviations. Okay? And this is sometimes called the empirical rule, or they call the 68, 95, 99.7 rule. Okay? So you can remember it that way if you'd like, so you never forget. And here's why it matters clinically, right? So if 95% of people are within, 2 standard deviation, okay, that means that only 2.5%, let me explain this, because you have 95%, right? 95% within 2 standard deviation. That means, right, that this wingtips right here, these wingtips, right? So you still have 5%, right? 95, that's 5, or 100%. You still have this 5%. Where did the 5% go? These wingtips is where that 5% is. But they're going to trick you. They're going to make you think that 5% are in both sides. No. It's going to be split in half. It's going to be 2.5 here, and it's going to be 2.5 there. Okay, so 2.5 are above that cutoff, and 2.5 are below that cutoff. And that's why so many studies report results as 95% confidence interval. It's a way of saying we are 95% confident that the true population mean, one we just talked about, lies in this range. Okay, and those tails here with 2.5 and the outliers are the edges. Those are the patient we often consider more abnormal and worth investigating further. Okay. Let's go to something. Now, until now, we focus on the normal distribution, but in real data, we often see other shapes. Okay. We have our negative skew. Negative skew is also another name for left skew, right? So they like this especially on step 1. This happens when the tail of the curve is pulled towards the left. Okay, meaning that there are more higher values and few low values. So there are more higher values, so they're pulled towards the left, right? So this towards this left. Sorry, negative skew. They're pulled towards the left, right? And an example of this is body weight. Most people fall into higher weight range, right? Most people fall into higher weight range, while only a small fraction are extremely underweight or malnourished. Right? So most people fall into higher weight range, while others, okay? Now in positive skew, we have, which is another name for right skew, right? Positive skew, right skew. And the tail of the curve is pulled towards the right. Meaning there are many lower values, and fewer high values. And an explanation of that is income distribution, right? Most people can earn modest incomes, while only a few are extremely wealthy, pulling the curve tail to the right. And then we have our bimodal distribution. Instead of one central peak, like our normal distribution, okay, there's 2 And this usually means there are two distinct subpopulations in the data. And a good example of that is Hodgkin's lymphoma, which shows peaks for both young adults and older adults. Okay, so younger adults might get it, and then old adults as well. There's two subpopulations. And then we're going to talk about statistical hypothesis a little bit later as well. And this is another picture of bimodal distribution, non-normal distribution being right. So for memory trick, being right is always a positive thing. Okay, a positive skew. And then now, let's tie this back to accuracy and precision, okay, with the curves examples that we see here. I wanted to get you guys to interact with me here and ask you what you guys think of some of these curves. Can anyone tell me about, let me see, because I want to block this answer. Can anyone tell me about curve D? What do you guys think of curve D?
Wouldn't curve D be our most accurate and precise because our standard deviation is closer to the center?
So it's going to be, so the small, so D is small standard deviation, right? The data is clustered tightly around the mean. So it's going to be very precise and reliable and also accurate. So yes. What about curve B?
That would be least precise, right? Because it's far from the population mean.
Right. So the data are clustered, right? But not near the true population mean. Yeah. So this is the population mean. It's far from that versus curve D, where it's at the center. So this is going to be precise but inaccurate, right? Because it's far from our population mean, correct? What about C?
It would be low precise and low accuracy because it's so far out.
Right. So it's very spread out, right, with larger standard deviation, right? So less precise than A. Okay. What about A? And last one.
Is it accurate but not precise?
Right. So widespread out with larger standard deviation, right? So it's spread out, but centered on the true population mean, right? Because it's still right there at the population mean. So more accurate than precise. So basically by looking at distribution shapes, you can visually connect back to concept of accuracy versus precision, right? The one that we talked about in the very beginning and how that relates to our distribution here as we started earlier. This shows you how all these ideas build on each other. And I want you guys to really think that way. I want you to think about this. These are not separate concepts. They're all connected. And I want to show you how they are connected. And I hope that's what's happening right now. And you guys can understand these concepts. Okay. Let's see. Do you guys want to keep going? You want to take a 5-minute break? I know we've been doing this for at least 40 minutes.
We can keep going, I think.
I'm good. We can keep going.
I like it. I like this group.
All right, let's do it. So at this point, you might be wondering, well, why should I care about all this stuff? Right? Why does it matter? Why do I need to know all of this? It's hard to understand. So the reason is that these concepts directly inform which statistical test we choose when analyzing the data, right? And that shows up both on the USMLE and in real research, right? So here's the first big question point, right? So here's your big, so from here, let's do this from here, right? So your first big question is, are you comparing means, averages of a continuous variable, or are you comparing proportions of people in categories? Proportions are just percentages. Okay, example of a proportion question. What percentage of patients who died from COVID were low income? Okay, that is comparing proportion. Now, mean question. What is the average income among patients who died from COVID? This is comparing mean. Okay, so both are getting at related questions, but they require different statistical tests. Okay, I just gave you a, we're talking about one disease, COVID, but we asked two different questions that will be addressed by two different statistical tests. Okay, again, one said proportion, meaning percentage, and the other is asking about means. So if you're comparing proportions, like categorical data, right? So if we're comparing proportion here, we go down, we ask ourselves, is that a big sample size, right? This is what we talked about earlier. Do this study have a big sample size, or does it have a small sample size, right? You will use a chi-square test for a larger sample size, okay? And you will use a figure-exact test when the sample size is small or when expected counts are low. Okay, so if you're comparing means now, let's go up here. We're comparing means, right? The question is, what is the average income among patients who died from COVID, right? Ask, are these the same individual measured before and after, right? So are these the same individuals? So there's before and after, right? An example of that would be, there's one person, they're working out, they want to have weight loss. And then there's a before, same individual versus after, okay, versus after. And so in that situation, right, you would go down here and use same individual followed over time. You would do a paired t-test because it's the same person. You're just going to compare before and after, okay? This is important because they're going to get you with an independent paired t-test. You're going to be like, what is an independent paired t-test? I know what a paired t-test is. I know that was me. Or so you have the, or you can ask, so is it the same individual? Or, are these independent groups, right? Independent groups or independent samples or different people, right? So if there are two groups that are not, that are different independent groups, you're gonna do two sample t-tests. And a two sample, and this is the thing about USMLE, sometimes they have multiple names for the same thing. It's like wild, So a two sample t-test is the same thing as an unpaired t-test and an independent t-test, okay? But a paired t-test is certainly different from independent t-test or a two sample t-test. So just keep that in mind, okay? That they have multiple names for things. And then if there are more than two groups, you have to consider an ANOVA analysis of variance, meaning like, three, means, comparing like more than two means, and these ones are comparing two different means, and you're comparing proportions. So keep that in mind, okay? We're gonna do some questions on that as well. And this is gonna make, reinforce the information that we're learning right now. All right, so let's do the next slide. So I want you to remember, when you're thinking about a chi-square test, right? Think proportions, okay? When you're thinking about, I need you to think percentages, proportions, okay? And then a test or an ANOVA, I want you to think about means, continuous data, right? Means, analysis of variance. And then paired tests, same people before and after, right? Paired tests, same people before T is meant to, same test, right? Same people before and after for paired and independent for separate groups, okay? So that's just a quick summary. All right, now let's talk about Pearson correlation coefficient, which is usually called R, question mark, right? So
Dr. Kimble, just a quick question before you continue to the correlation coefficient. If we go back to the previous slide or the one before then, I know that we're saying that proportions is categorical and means is numerical, but I've seen in a bunch of UWorld questions where they use qualitative and quantitative as
yeah,
the phrasing that to describe
oh, sorry.
no, it's fine. Of like their phrasing. And sometimes it's like a qualitative value plus a quantitative. Did I say that right? Qualitative and quantitative. And then it's like quantitative, quantitative, or qualitative and qualitative. Would you be able to like just go back to the previous slide and just say like this is qualitative, quantitative, this is quantitative, quantitative. Do you get what I'm saying when I ask that? I'm not sure.
Um,
Like for example, they would give you like a study
I do
and
know what you're saying, sorry.
you do. Okay,
But
good.
the way that I would, so a qualitative data is the same as a categorical data, okay? It's basically going to describe like qualities or categories of things and not numbers, okay? So like, for example, an ordinal categorical with order would be like pain scale, like mild, moderate, severe, right? So that would be qualitative, right? And then a nominal categorical order would be like blood type AB, or O, or gender or religion. So that would be qualitative slash categorical data sets, right? Does that make sense? Is that what you're asking me?
Um, so sort of there's like a graph or a table. I'm not sure if anyone else has seen it, but it's like on UWorld where they break down the different quantitative and qualitative, so like your means and your proportions, but they would make it as though the independent variable can either be qualitative or quantitative, and then the dependent could be quantitative or qualitative. And then they showed you, okay, this is t-test, this is chi-square, this is logic regression, this would be a nova, and that's like the table that I'm thinking of. I mean, if I find it, maybe I could like screenshot it and put it in the.
Yes. So when I remember that's like the what you're talking about. But what I want you to think about is when you see qualitative, just think of categorical, and categorical qualitative are also same thing as proportions and percentages. Okay. And then quantitative, your numerical data, right? These are your means, right? Your whole numbers, number of hospital visits, right? Continuous variable, fractions, height, weight, blood pressure, serum glucose, things like that.
Thank you.
But you can also send me that. Send me if you, we can talk about it more. But I want you to think about it in that way. Again, they have multiple names for things. I know that I'm explaining this here as like means versus proportion, but means you want to think about quantitative, something that is numerical, right? And that's what they're saying here, right? These are quantitative variables. And then you have qualitative categorical variables that you're comparing in when you're doing a chi-square and a Fisher-Exact test. Hopefully that answers some of your questions, but now we can talk more about it. The Pearson correlation is our last slide. Okay. So let's move to that. Okay, so the Pearson correlation. So the key concept in Pearson correlation is that the value of R is always range between negative R or R. Negative 1 or positive 1. Okay, and positive or R equals positive 1, which is here, positive 1, which tells us the means are perfect positive correlation. As one variable increases, okay, the other increases in perfectly straight line. So you can see these data points perfectly in sync with, okay. And then you have R negative 1, which is at the complete opposite of this chart, where the means is a perfect negative correlation. So as one variable increases, the other decreases in a straight line. So a good example of this is as women age, fertility rates decrease, okay? And R of 0 basically means there's no linear correlation at all, right? The two variables move independently, okay? And the visual walkthrough here, you can see, right? So R plus 1 is a perfect upward line. Every increase in X equals proportional increase in Y. R plus 0.3 here is a weak positive correlation, just a slight upward trend. And then plus 0.8 is a weak, is a strong positive correlation, still mostly upward with some scatter, right? So some scatter, you can see some of these data points are outside of the line. Best fit, okay? And then R0 negative 0.3, weak negative correlation and a slight downward slope, right? And you see all these more scatter in this data set. And then our negative 0.8 is a strong negative correlation and a clear downward trend, right? And then as you see with negative 1, a perfect downward line, meaning 1-to-1 inverse relationship. And so this is an important tip, especially for epidemiologists or, you know, public health practitioners. They will take it very, very personal, as I do, and I probably won't correct anyone. But remember, when we're talking about correlation coefficient, correlation does not equal causation, okay? Most often for public health practitioners, we're very careful of saying causation. Just because two variables move together doesn't mean one is causing the other, okay? And a classic example of that is that ice cream sales and drowning rates both go up in the summer, you know, and not because ice cream causes drowning, but because the co-founder is hot weather and more swimming. So sometimes you'll see, and sometimes, you know, and again, just like I was saying, public health practitioner would say, there is an association, okay? In research, an association is present, not this cause that. So just very, very careful when you're communicating with people, especially when you're doing presentations at research conferences, say association. All right, so in summary, Pearson R tells us how tightly the two variables are linearly related, in which direction. And the closer R is to either +1 or -1, the stronger that relationship is. All right. right, that is our last slide. I'm going to try my best to answer all of you guys' questions. If you guys have questions, now is probably the time to do that. And then we're going to do some biostats practice questions from the MBME and from AMBOSS as well. So we can reinforce all the information we're just exposed.
Matt, if you can, I've sent you the table. If you could post it. I don't know if I have ability or access to do such.
Yeah, yeah. Give me 1 second.
Thank you.
All right, bet. Yeah, let me see if I can post this. Yeah, guys, give me 1 second. I'll post this in the group. I think this is very nice.
Send it to me in a text.
Yeah, I can. Yeah, I'm about to send it to you.
Yeah, it would be, if I can see it, that would be better.
Okay. All right, I just texted it to you.
Thank you.
And then I'll send it in this chat if you guys need it. Teams, calendar, 6. 1 second. Okay, yeah, I don't know. I can't post it in the actual chat, but I sent it to you, Mabel, the picture.
Okay, let me see. I'm so waiting.
So did we had a question about the picture? Is that what it was?
For me, it was just more so I get the seeing the values as numerical versus categorical, but I feel that at times with the year old questions, they'll give you like a qualitative
Mm,
uh or categorical, and then they'll give you a quantitative. And sometimes for me, just remembering, okay, if it's qualitative, if the independent variable is qualitative, but the dependent is quantitative, this is the test
mhm.
specific have to look for that's being tested.
I
So
got you.
that's why I was asking if we could use the the words qualitative and quantitative so I
Yeah,
could
yeah, that's fair. Okay, cool. Maybe would you get it? I think I just sent it to you.
Yeah. I see it.
Also, great job, guys, with the with answering the questions that Mabel had. These are very difficult questions, and these are questions that you're really going to see, I think, are very high yield because I think they're, very commonly tested concepts. And so I'm very happy that you guys are, knowledgeable. I'm kind of jealous because I feel like when I was at your stage, I didn't know these things. So, you guys are definitely already doing better than I am, at least in that stage. So, um, for what it's worth, but really, really happy. And I'm also very happy for the participation. It takes a lot of guts to, we have a big group here, so it's nice that you guys are willing to speak up and ask questions and kind of answer some of the questions that are being asked. So I really appreciate it. While Mabel's looking for that, do you guys have any other questions? This can pertain to biostats. It also can, or epidemiology. It also can pertain to, I know everyone's in a different place, but whether it be residency apps, because I know those are currently going out shortly. It can be fellowship questions. It can even be like clinical rotations. Like I said, we even have some step one students on here. Do you guys have anything that I can answer?
Yeah.
For you guys.
Can someone help me with the Hardy-Weinberg equations?
We got more calculations and stuff over here. Yeah, I'll have to find a chat or a group or a picture for that one.
Okay.
I'll find something for you though.
Okay. So I'm gonna try to bring this thing up and see if I can answer this question. Okay, sorry, now you guys can see my screen here. Oh, can you hear me? Okay, so the way I would deal with this, um, the way I would deal with this would be I would ask myself, like, identify the types of variables, right? First, you ask yourself, like, figure out your dependent variable, like your outcome here. So your dependent variable is your outcome, and your independent is your predictor. Okay. So your first step is to figure out your dependent variable. Okay. So if it's categorical, right? If it's categorical, like yes, no, group labels, right? We say we use chi-squares or logistic regression. Okay. Now, if it's numerical, like measures of lab and values, right? We use t-test for this numerical, like numerical. So I'm gonna say numerical and category. We're gonna use the t-test or the ANOVA or linear regression, right? And we haven't really talked about linear regression, so this is probably why this is kind of confusing. So, and then second, right? So first, dependent variable, look at your outcome. Second, you look at your independent variable, your predictor, right? So if you have a outcome that is in percentages, right, or proportions, you're saying, okay, I have to look at a chi-square test, right? If you have an outcome that is a categorical, a proportion or percentages, then you have a qualitative independent predictor, independent variable, then you're doing a chi-square test or a logistic regression. In this case, we're going to focus on chi-square test, right? Now, if you have an outcome, a dependent variable that is categorical, okay? Here you have categorical, and then you have a numerical independent variable, right? So if you have qualitative and then qualitative, right? Then you're going to use t-test and ANOVA, okay? Now, if you have a numerical, like meaning quantitative, and a categorical, then you're going to do, you have a numerical and you have quantitative, then you do logistic regression. And again, we haven't talked about this yet, and so we're gonna make more sense of that later. And then when you have a both quantitative, we do correlation and linear regression. So if you have a quantitative outcome and a quantitative independent variable, then you're going to do linear regression and correlation. Again, if you have a outcome, a dependent variable that is first categorical, and an independent variable, your predictor, and categorical, then you do chi-square. Okay, and then categorical outcome with a numerical, well, categorical independent variable, and then a numerical, then you do the test and ANOVA. Okay, so the short mnemonics I would do for that is like, if you have cat, you do chi-square, if you have that, I would compare means, so t-test and ANOVA. And then if you do NumCat, which we didn't talk about today, then I would do logistic regression. And then if you have, sorry, these are really weird mnemonics, num, you do correlation and logistic regression. And again, this cat is just like, qualitative, then qualitative, quantitative, and then quantitative, qualitative, and then quantitative. Hopefully that answers the question.
That helped. Thank you.
Okay. But what I do want to do before we leave today is try to do like a few questions if possible, so that we can bring this home for everyone. All right.
Perfect. All right, let me just go through the chat. Sorry, I just kind of logged out for a second. Mabel, did you answer any of these questions or did you see any of these questions? We had a couple.
Oh, I had not.
It's all good. It's all good. Let me read them for you. Thank you for, so Krika said, thank you for going over this. Will we be able to get some examples of questions we would get from this chart as well?
Yeah, we're doing that right now.
So I think that was a couple minutes ago, so maybe I'm a little too late.
Yeah, we're doing that right now. So this question is asking us about accuracy. This question is asking about the test that we just went over, positive skew, basically all the things we just went over. So we can start that, if that's what you guys want to do now. I know I see Karim saying, I'm reviewing how sensitive isn't true when we shift diagnostic threshold to the right and left. Sometimes the way these values change can be confused, especially how they flip depending on the cutoff. Yes, and I have a trick for that. And I think once I explain that trick, I don't know if we're going to go over it today, but I have a trick for that. And then you will never be confused ever again. But let's go over these questions. All right, so do we have any brave volunteers to read this question?
I could read it.
Okay.
Okay, so two researchers wish to determine the prevalence of hypertension in a metropolitan city. The first researcher measured the blood pressure from 1,032 inpatients at a tertiary care hospital for geriatric patients in the city, which is study A. The second researcher performed community blood pressure screening on 1,003 people in study B through simple random sampling. Both studies are conducted using calibrated sphygmomanometers from the same manufacturer. Compared to study A, the result of study B is most likely to have which of the following properties with respect to the researcher's initial goal. I think because the population of study B is less, would there be
So the scenario is blood pressure measured in 132 geriatric inpatients at a tertiary hospital. So this sample is not representative of general city population, right? With bias towards the sick and older patients. In study A and in study B, blood pressure measured in 1,003, right?
Yeah.
Randomly selected people in the community, right? So that sample better represent the general city population. Okay, and the question basically asks compared to study A, what property, what property in study B most likely to have with respect to their goal, estimating citywide prevalence of hypertension. So,
They have smaller sample size.
okay.
So I would that be lower risk of type 1 error?
So study A only looked at hospitalized older patients, right, which doesn't represent the city. So that means its results are biased, right? So study B randomly sampled people in the community, right?
I see.
So
Okay.
that is more representative and closer to the true prevalence.
Mm-hmm.
So I get where you're trying to get at. Like you're saying that it lowers the risk of type 1 error. Um, not this question is not getting at that.
Would it be D then, lower risk of measurement bias?
So measurement bias would occur if one study used a faulty instrument or poor measurement technique, right? But both use the same calibrated, you know, symphoganometers. So there's equal risk, right? And for C, you're lower risk for type 1 error. So type 1 error is false positive, right? And not directly related here. And this depends on statistical testing threshold, right? So that would be gone. That would be out. High statistical power. Power depends on sample size and variance, right? Both have basically 1,000 participants, so they have similar power, okay? And then B, higher precision. Precision is repeated, again, repeatability, how tightly clustered measurements are, right? So precision depends on sample size and consistency of measurement, not whether sampling was random, right? So not there, so both have similar sample size. So precision is similar. So we end up with higher accuracy, right? Accuracy is the closest to the true population value, like the true population mean. Like since study B used random sampling from the community, it is more accurate, right? For estimating prevalence in the whole city, right? And study A is biased because it's hospitalized patients in city versus citywide population. So this would be the correct answer. Does that make sense?
Thank you.
Thank you for being so brave, Nisha. Really appreciate it. So this is the answer. So yeah. So basically the same thing I've said, but just explained differently. Yeah. So I'm gonna give it to Dr. Simpson here. He's gonna take over.
Yeah. Sorry, guys. I knew how important this session, well, first of all, I know how important this session is. Next off, I want to thank Dr. Kimble for that amazing talk. I actually was taking some notes over here by myself, trying to figure out, I'm always done with my boards, but I'm still over here trying to relearn things. So that way, when I tutor you guys, that I can maybe try and teach you some of these techniques that she's been kind of teaching you guys. But if you guys are interested in more of these sessions, you guys have my contact information. Feel free to just reach out. Dr. Kimball is now joining us as one of our lead tutors. So if you guys are interested in more specific biostats and epidemiology courses, let us know. That's something that she's offering. She's also now tutoring for our Step 1 students as well. So if you guys are interested, feel free to either fill out a contact form on on our website, or you can just message me directly, and we can definitely get you guys set up for that. Otherwise, hopefully, we can do another one of these webinars in the future, because I really think it's going to be beneficial, and I think you guys are going to see a lot more improvement in your scores, just off of this one hour session because as Dr. Kimball was saying, there's so much more to this. So we can't really fit it on 1 hour, but thank you guys for joining us. I'd love to see some familiar faces, some old faces. Like I said, feel free to reach out at any time. I'll shoot my email down here so that way you guys have it if you need it. And then otherwise, just be on the lookout on our socials for more upcoming webinars. But thanks you guys for joining.
Thank you so much, everyone, and thank you for participating. I know it can be intimidating, but I wish you guys luck in your boards. You can do this because I did it. You definitely can do it. So reach out to us. We're here to help you get through this.
Thanks, guys.